All right, so let's go get ahead and get started. We're going to go ahead and cover our new section called implicit differentiation. And we're also going to learn some probably new derivative rules. I'm probably expecting this today's lecture material to take probably 2 days. We'll probably today introduce implicit differentiation. And then tomorrow, I think we should be able to get to inverse trigonometric functions. All right, so let's start off with what does it mean to do implicit differentiation? So we're familiar with the word differentiation. It just basically means take the derivative. But now we got to figure out what the heck does it mean for implicit differentiation. So to introduce this, I'm going to go ahead and say, let's compare what does it mean for it to be an explicit form versus implicit form. And unfortunately, this got a little bit messed up in a transfer. This is explicit. I guess I'll rewrite it so that it's a little bit clearer. So on the left, the explicit form. This is if I have something like y is equal to x squared over 2 plus 1, for example. So, and here on the right, I have implicit. For example, I might have 2y minus 2 equals x squared. So if I showed you this little versus thing, what do you think is the big difference between explicit versus implicit form? That's one thing that we could note, but what's one thing I noticed about the variables for the explicit form versus the implicit form, how we wrote them? Yeah, so on the left, I have very directly, this is y. Y is equal to x squared over 2 plus 1. In other words, I've very explicitly stated what is y. Whereas in the right, I don't exactly have y is equal to whatever, x is equal to whatever. I just have it, here's my equation with x's and y's. So if I compare these two, these are actually the same equation, right? For example, I can multiply everything by 2 and then subtract 2 from this equation and get the right side. Or for example, I can solve for y and get to the left. So looking at this example that I've given so far is an example of an equation that I can go back and forth between explicit versus implicit form. In other words, I can solve for y if I wanted to. However, we know that this is not always necessarily true. There are a lot of equations where I can't solve for one of my variables explicitly. For example, right here, if I have y to the 5th minus 5y plus x equal to 0, there's nothing that we can really do to say y is equal to something that only has x's. In other words, you can't isolate y here. I could isolate x. I could get x is equal to something. That might be good. But overall, I can't really get a y is equal to something that is strictly in terms of x. So if I look at that example, y to the 5th minus 5y plus x, even though I can't solve for y, I could still get the derivative of y somehow. And that's what we're going to be looking at today. Whenever I don't just have a plain y is equal to whatever, how do I get the derivative of y? And actually, even though we're focusing on this implicit differentiation, this will actually help us in some cases whenever we want to deal with something explicit. All right, so this is just again comparing what does it mean to be explicit versus implicit form. The long story short, explicit means I have a variable equal to everything else. Implicit is whenever I don't necessarily have that. So I'll give y'all some time to copy down anything as needed. So I would say that y'all know how to get the derivative of that left equation. Y'all would, if I gave y'all the explicit form, you could give me y prime, or you can say dy dx. So we're going to talk about how do I do something similar for the right side. And actually, despite the fact that it looks different, it's actually going to be using all the exact same rules that we've learned already, but with this one extra thing to add, technically multiply by. All right, so let's go ahead and move from here. Hopefully, there we go. Find dy dx, given that we have 225x is equal to y squared. So here I've just thrown you straight into an example. I'm going to do this in two different ways. One is one that we're familiar with already. And then after that, I'm going to show you how we're going to deal with this in terms of implicit differentiation. So if I were using my existing methods that we already know for derivative rules, I probably want to start off with getting my equation to be y is equal to whatever, right? In other words, I could take the square root of y, of y squared on the left and right. So if I took the square root, I could say, for example, y is equal to, if I want to be sort of exact, square root of 225x. Again, I haven't taken a derivative yet, but if I wanted, I could solve for y. So if I look at this, is this an explicit form or implicit form, what I've written here? Explicit, again, it's y is equal to whatever stuff with x's. And so we know how to get the derivative of this. Before I do that, I could, again, also write this as plus or minus, not square root, oops, plus or minus 225x to the 1/2 power. Again, haven't taken a derivative, but we know that we don't usually like square roots and stuff like that. So if I want the derivative, dy dx, or if you want, you can say y prime, what is the derivative of this expression that I have here? Anything else? Yeah, times 225. Because remember, we had to multiply by the derivative of the inner layer too, because of chain rule. So I have something that looks roughly like this, right? As my derivative. This is how we may have done it before. So this is trying to take the derivative through explicit, I'm gonna call it explicit differentiation. Now let's talk about what if I try to do this implicit differentiation. And I haven't really discussed it, but we're gonna see an example of it here. So this is one way that we can try to find the derivative. Now if I try to do implicit differentiation, here's how I'm gonna do it. If I look at this very directly from the beginning, clearly this is an implicit form. It's not y is equal to whatever, x is equal to whatever. What's the derivative of 225x? Yeah, derivative of 225x would still be 225. What's the derivative of y squared? Yeah, so first off, using power rule, we would get 2y. But we had to add one more thing in here, technically multiply by one other thing. What I'm going to do here is I'm going to multiply by a dy dx. Let's talk about why I multiply that there. This actually comes from chain rule. Because this is not a plain x squared, right? Usually if it's x squared, we just say 2x and we're done. But since it's not our standard x squared, my first layer, if you want to put this as a side note, my first layer is something squared. So derivative of that something squared would give me 2y. And then what's the derivative of a plain y? Yes, the derivative of y, we always say is dy dx. So this, you can imagine that the dy dx is actually coming from chain rule. One small thing I want to note also is, does anyone have an idea, why do I not bother doing the same thing whenever I take the derivative of x? Why is it whenever I do derivative of y, I need to write dy dx, but I'm not doing it for dx? So remember what this dy dx means. This just means the derivative of y in respect to x. Now this is what I'm about to say is not really a true explanation. But if I use that same idea, derivative of y is dy dx. Derivative of x, if you want to justify it this way, it would be like if we were adding dx over dx, which you can imagine would be like 1. All right, so I want the derivative, so I want dy dx. How do I get dy dx alone from here? What should I either add, subtract, multiply, or divide by? If I want dy dx alone. Are we subtracting it? So if I want dy dx alone, remember this is, yeah, I want the dy dx alone. Because remember my end goal is dy dx equal to whatever. I'm actually going to divide by 2y on the left and the right, giving me dy dx is equal to 225 over 2y. I claim that this is the same thing that I wrote on the left side, but why? Why is this the same thing as what I wrote over here? So it's actually going to be a very quick thing. I'm claiming that this is going to be an acceptable final answer. But if I look at this, what is y if I wanted to solve for it? Y is this plus or minus square root of 225x. Or you can write it like this. So if I wanted to fill this in, it's not something that you have to put in. 225 over 2, and instead of y, I can put that right there. Plus or minus the square root of 225x. Well, isn't that exactly the same thing here? Plus or minus, 1 half here. 225, 225. The square root of 225x on the bottom. Square root of 225x on the bottom. So these are actually still the exact same expression. Is that here my derivative has a y in it. This one is strictly in respect to x. So in other words, I'm taking this as my derivative, 225 over 2y. Yes, you can write y prime. The reason why I personally do dy dx is that actually is going to come in handy later on whenever we start doing integration towards the end of the semester. But y prime, equally justifiable. Some people like writing y prime just because it's a little bit nicer to look at. All right, so any questions about this first example? The big thing that we're pulling away from here is if I take the derivative of y, I need to write dy dx. All right, so let's go ahead to our next one, or next slide. Let's get y prime, given that sine of y is equal to x minus 9. So the first thing I'm going to note here is I definitely don't have a simple y is equal to whatever in respect to x. Could I get y alone? Yes, but then we're not familiar about how to get rid of that sign, really, and how to deal with the derivative of that. So we're going to keep this in its implicit form. So in other words, we're just going to take the derivative right off the bat of this expression. So on the left side, what is the derivative of sine? Yeah, we have derivative of sine is cosine. Because of chain rule, and because I took a derivative of a y term, I had to multiply by dy dx, or let me use the same notation here, times y prime. Again, you can say y prime or dy dx, they mean the same thing. And I claim that's what's happening on the left. Again, derivative of sine, we get cosine. And because of chain rule, I need to take the derivative of y as well, my inner layer. The derivative of y, we get y prime. So I'll emphasize what I said earlier. When I take the derivative of a y expression, I have to multiply by that. You can say either y prime or dy dx term. All right, so that's the left side. What's the derivative of the right? What was that? I think I heard two different answers. Yeah, so let's see. Derivative of x, we get 1. Derivative of -9, we get 0. So 1 plus 0 or just 1. All right, so how do I get y prime alone now? Yeah, we're going to divide by cosine of y, giving me that my derivative of y prime is 1 over cosine of y. And this would be an example of something that would work. It would be acceptable. If you're a little bit familiar with trig, you could also technically write this. It's technically still the same thing. This is technically equal to secant of y because of reciprocal identities. But if you're not familiar with that, don't worry about it. I'm not too concerned about all of these particular identities. But yeah, we got y prime. Notice here that my derivative has a y in it. Before, whenever we had explicit differentiation, our derivative always had whatever x is. But in here, it's possible that my derivative has y's and x's, depending on what we're looking at. All right, so any questions for this example 2? And then make it implicit. Yes. All right, so we're done with example 2. Let's just go over the general steps that we have here. Again, you don't have to write this, but it's a nice little general thing that we have. So if I have an equation in implicit form, again, maybe I don't necessarily have y is equal to whatever. Then if I want to solve for dy dx, or you can say y prime, whatever your preference is, then generally I follow these steps, or at least for the problems that we are working with. I differentiate as normal. Again, any of our derivative rules, power rule, product rule, trig functions, anything like that. However, if I take the derivative of a y term, or in particular a y, I need to write dy dx immediately after. And we saw us doing that in those previous 2. Step 2 is if it has anything that has a dy dx needs to be on one side. Anything that doesn't have a dy dx needs to be moved to the other. The reasons we do that is that on the side that has a dy dx, we can factor out my dy dx and then solve for it directly, usually by division. And so you're going to see what I mean whenever we get this example. This is just going to be a backbone for what our example 3 is going to look like. So again, if you want, you can take a picture of this, but really it's just more or less of a backbone for our problem. So let's go ahead and look at this example 3. Example 3. That will come up. There we go. Let's go ahead and throw in some derivative rules that we know about and everything like that. Find the derivative of y, given that we have 9x y squared is equal to 5x cubed. So it looks like the main issue that we're going to be seeing here is what's on the left. So what rule do you think I'm going to end up using to get the derivative of the left side? We will be using power rule. Anything else? A product, right? Because I see the product of two expressions. If I'm using product rule, what can I label as my first? Yeah, we can say 9x. Let's list that as our first. And then second can be the y squared. So let's go ahead and get the derivative. So product rule states that the derivative of a product is, someone remind me, what is the product rule? First. Yeah, first d second plus the second d first. So following through with product rule, I have the first, 9x, not a problem. That's first. Next is d second. What is the derivative of y squared? The derivative of y squared. Yeah, we get 2y. Bless you. Is there anything else I need to add on for the d second? Yeah, dy dx. Because remember, I said if I take the derivative of a y term, I throw on that dy dx. Here I just said the derivative of y squared. So I had to put 2y and then dy dx. Or again, if you want, you can put y prime. It doesn't really matter. So I have first d second plus the second, so plus y squared. And notice here, why did I not put a dy dx right here? Yeah, it's not the derivative of y. I just copied down my y. It was just the second. Again, we're only writing that dy dx when I say I take the derivative of y. And then I need the d first. What's my d first? Yeah. Yeah, so derivative of 9x, we get a nice 9. So that's my left side. And then this is equal to, what's the derivative of the right? Yeah, 15x squared. We don't have to worry about dy dx because first off, there's only x's on that side. All right, so this is me doing my implicit differentiation. We take the derivative right from the start without moving anything. All right, so I'm still not done yet because again, my end goal is let's get dy dx alone. So depending on how you want to write this, you can either give me a simplified form or not. Maybe let's go ahead and just simplify a little bit because here the simplification is a little bit quicker. So on right here, 9x times 2y, 9 times 2, I get 18xy dy dx. Again, here I'm just multiplying it. If you want to leave it separate, that's completely fine. I'm doing the multiplication because here we're not really multiplying really big, complicated things. Plus y squared times 9. Yeah, we just get 9y squared. And we get this so far. All right, so Again, I want dy dx alone. What's the next thing I should probably do? Adding, subtracting, multiplying, dividing. Yeah, we should subtract 9y squared. I'm running out of room here, but subtracting 9y squared, we get 18xy dy dx. Oops, I don't know why I wrote 18. Dy dx is equal to 15x squared minus 9y squared. So I can't really combine the x squared and the y squared. These are different terms. What is the last thing that I can do to get dy dx alone now? Yeah, so I can divide both sides by 18xy, giving me a final answer of, let's see, 15x squared minus 9y squared all over 18xy. And I claim that I'll take this as my final answer. I know I'm done because I have dy dx alone. If you didn't combine these, then the only difference is that you would have dy dx equal to 9x 2y. You would have it in its factored form instead of the multiplied version. So we're getting to the point where we're starting to play around with some more letters here and there. X from the left-hand side. So the reason why I'm not going to eliminate, are you talking about from the beginning? Why can't I just divide, for example, by 9x? So that is a good thing to note, but here's the reason why I'm not actually going to divide by 9x. So let me see. Let me write it right here. Oops. I'm going to do a random side example again. You don't have to necessarily write this. X plus 1, x minus 2 over x minus 2. Let's say you had something like that. Usually we would say, all right, I can go ahead and cancel out because I have x minus 2 on the top and the bottom. And you would get x plus 1. This is great. We didn't break any rules, but there is one problem about this. This equality is true everywhere except for one value. If I plug in 2 on the right, I get 3. But if I plug in 2 on the left, it's undefined. So these functions that I have, yes, they are equal everywhere except for one number. So right here, whenever I divide by 9x, yes, it's going to be the derivative the same almost everywhere, but there's going to be one number where they're actually different from each other, which you'll see is 0. So to get the most complete idea of this function, it's better if we leave it alone. There are going to be some examples where we do some manipulation beforehand and then do the derivative. But generally, I kind of want to avoid dividing by terms because that brings some slight nuances that we might be missing. All right, besides that, any other questions about this example 3, how we got the derivative? All right, so I'm going to go ahead and clear the screen and move on to the next one. Okay, so something like this. Again, give me the derivative of y, given that I have e to the xy power is equal to 5x plus 7y. I'll give y'all a moment to write this down. And let's talk about how we'll take this problem on. Again, the first thing I'll note here is I definitely can't solve for y. I have a y in a power, and then I have a y sitting alone by itself. And it looks like most of my issues are going to come from that left side, that e to the xy power. So looking at this, let's focus on the left side, e to the xy power. Just as a refresher, what is the outer layer of that expression? E to a power, right? It's e to something. And then my inner layer would be x times y. All right, so what is the derivative of e to some power? Yeah, e to, in fact, the same power. So that's the outer layer derivative. And now I need the derivative of x, y. What rule do I need for the derivative of x times y? Product rule, yeah. In this case, where x is my first, and then y is my second. So again, to get the derivative of the inner layer, xy, we need the product rule. And by now we're familiar with product rule. Product rule states that the derivative of that product, x times y, is the first. So I have x. What's my d second derivative of y? Yes. So derivative of y is 1, but because it's a derivative of y, we have to write dy dx. So again, first derivative of y, which is just dy dx, plus the second, which is just going to give me a y. And what's my d first here? Yeah, so the derivative of x, we have 1. So I'm not going to bother writing times 1 because, times 1 doesn't really change anything. If you want, you can put it for notes, but I already know times 1 doesn't do much. All right. Then I claim that I have the derivative of the left because I only had 2 layers. The outer layer, e to a power, the inner layer being xy. All right, and then that was a harder part of this problem. What about on the right? What's the derivative of this entire right side? 5 plus 7. Is there anything else? Yes. It'll be 5 because derivative of 5x is 5. And then the derivative of 7y is 7 because of power rule. And we have to put that dy dx because, again, I just took the derivative of y. If you're ever going through this and you're saying, I took the derivative of y, you have to put that dy dx immediately after. All right, so I've done all of my differentiation. Now my job is getting dy dx alone. So I'm going to walk y'all through this one. So first off, we're noticing that there's 2 dy dx's here, right? Let me go ahead and get rid of these parentheses by distributing my e to the xy. So I'm going to take this e to the xy and distribute it to both terms. Because I can't really move anything here without dealing with this e to the xy. So for this first one, I just get x e to the xy dy dx. So x dy dx times e to the xy. Just multiply them together. Plus e to the xy times y. I'm going to write as y times e to the xy. I like writing it in the y and the x's in front, just so that we don't get confused that, like if I write y after, sometimes there might be a confusion, is that multiplied or is that in the power? And on the right side, I'm not changing anything. Y dx. All right, so again, the reason I did that is that allows me to now add and subtract to move stuff around. If I try to add or subtract and move stuff around here, then I'm pretty limited in what I can do. So do y'all want to move the dy dx's to the left, or do you want to move the dy dx's to the right? There's no wrong answer for this one. Y'all said right? Yeah, so let's say, for example, I move the dy dx to the right, and the stuff that doesn't have a dy dx, let's move it to the left. Yeah, the signs are going to change. Um, the reason why it's not going to matter is that the sign changes for both ends. So like it's going to do a net canceling out. That's why sometimes your answer might look slightly different, because some of y'all might have a negative on top and a positive on bottom, and some of y'all might have the reverse. All right, so let's move the dy dx's to the right. Dy dx. So I'm subtracting this from both sides. E to the xy dy dx. And for the sake of just doing this quickly, I'm going to move this 5 to the left as well. So let's subtract 5. All right, so let's write out where everything moved. Let's write it up here. On the left, I've got this canceled out because I wanted to move it. And I'm left with y e to the xy minus 5, like so. On the right, 5 minus 5, that canceled out. And I'll have 7 dy dx minus x e to the xy dy dx. So again, anything that had a dy dx, I put it on one side. If it did not have a dy dx, I moved it to the other. I'm sorry. Oh, so right here. So I'm sorry. Yeah. Nah, you're good because I have bad hearing too. Oh yeah, so you're talking about, just to be clear, are you talking about what I wrote on this line? Yeah, so I'm just adding and subtracting to move stuff around because like here, I wanted to move this 5 to the left and subtract it. And uh, I subtracted this to move it to the right because my end goal is getting dy dx alone, right? So anything that had a dy dx, I just put it on one side. You notice how here this 5 doesn't have a dy dx, so I just moved it over to the left. And then this was already on the left. One thing I'll note for y'all is y'all could have moved this one to the right, for example, and then this one to the left. All that matters is that all your dy dx's are on one side. Because if I keep them separate, then I can't really get a single dy dx, for example. All right, so here and then I just move this all the way up here because I don't have any room to write it down here. So why did I want to put all my dy dx's on one side, like what I have up there? What was that? Yes, so we want the derivative of y on one side, but in particular, there's two dy dx's. I only want one somehow. So what I'm going to do here is, since both of these have times dy dx, here and here, I can factor out a dy dx. In other words, y e to the xy minus 5 didn't change anything there. I can take out a dy dx, giving me 7 minus x e to the xy. So again, both of these had times dy dx. It's kind of like if I gave you this, plus 5xy. Here you can take an x out from both of them. Like you could do this. You can take out an x because both of them were times x. I did the same thing here. Both of these had a dy dx, so I can take it out from both of them. So looking at this, I claim that there's only one last step for us to finish this problem. How do I get that dy dx to be completely alone? Yeah, we're going to divide the left and the right by 7 minus x e to the xy. And our answer will look ugly, and that's intended. So on the right, this is going to cancel out, leaving me with dy dx. For the rest of this, I'm just going to leave this completely alone. There's nothing for me to really simplify nicely here. I'm just going to rewrite it. Y e to the xy minus 5 over 7 minus e, x e to the xy. And then I see that dy dx is alone. I'm going to do a recap of this also in a moment, because we did go through a lot of steps here. Though I do want to emphasize one particular thing here. We can't, because it's a binomial expression. The same reason why we can't do this. Seven. We can't do something like that, right? The same reason why I just can't cancel out the e's, because the top is one whole item, and the bottom is one whole item. I'm not just choosing one little piece out from one part. All right, so the thing I wanted to emphasize here, the actual calculus work was going from here to here, because this is where we did the derivative. After this step, it was actually algebra manipulations. Because here, this is just multiplying. Here is adding and subtracting. And then here was factoring, for example. So we can see here the actual calculus used one line, but the algebra work was the majority of our problem, getting that dy dx alone. So the first thing I know is that it's going to take a while getting used to all these dy dx's. Where are they coming from? Again, the core of it is anytime I take the derivative of y, I have to write dy dx. Like right here, add first, and then the derivative of y, plus the second. Whenever I said second, that wasn't taking the derivative of y, and that's why we didn't write that dy dx. So usually for this section, the most difficult thing for a lot of people is when do I write dy dx and when do I not need it? So that's something that we'll have to practice a little bit over time. We'll probably spend maybe another day or 2 days on this topic, really so that we can get it down for all the other sections that I can use this. Last thing I'll note is, can anyone give me a reason why I might need implicit differentiation? Maybe not necessarily an application, but why might it be necessary? Yeah, for example here, we can't solve for y, no matter how I rearrange this, add, subtract, multiply, divide. But even if I can't solve for y, I can still get the derivative, because this draws some type of picture if I want to graph it. All right, so we are out of time for today. I'll talk more about this tomorrow. If you do have any other questions, then obviously you're more than welcome to ask. Besides that, I'll see y'all tomorrow on Tuesday.